So before starting the lecture, I have to introduce the small CV of Professor Matthew. So Professor Mathew, right now the faculty of the Department of Mathematics in IIT Calicut. Professor Mathew completed his BSc and MSc in mathematics in the year 1997 and 1999 from the University of Calicut, and then joined NIT Calicut for his PhD program in the year 2003 and receiving the degree of PhD in the year 2009. And then Professor Mathew started his career as a faculty member of Government Engineering College, Kerala, in the year 2005. And then again he shifted his service to Government Brennan College in Kerala in the year, and he stayed in that college 2007 to 2010. And finally he joined NIT Calicut as an assistant professor in the year 2010. And right now, he is an associate professor on July 2022. Professor Mathew have published more than 183 publications. It is a very good number. In which 47 SCI papers and 56 Scopus Index journal and 33 in Q1 journals. His age index is 26, IQ index 55, and total citation of course Google 2834 citations. Until now, Professor Mathew has guided 17 PhD scholars, and right now 8 are currently pursuing for doing PhD. And Professor Mathew published 12 books in different publishers, completed several research projects. And mainly, Professor Mathew worked on this fuzzy graph theory. As well as Professor Mathew has been acted as 3 external and 1 internal examiners. Oh, sorry, 3 external projects and 1 internal project with total fundings near about 84 lakhs. So thank you, Professor Mathew, for your nice bio. So without taking more time from your presentation schedule, I request Professor Mathew to start your presentation. This is the time right now. Professor Mathew, start please.
Yeah, thank you for the nice words about me. Am I audible to you, sir?
Yeah, this audio.
Okay, fine, fine. All right. So I will share my presentation, then we'll see what happens. So what about my screen, sir? Is it visible?
Make it larger.
Is it visible?
It is visible. Just make it larger.
Okay, no issue. Then I will mute this. Is it fine, sir?
Yeah, it is fine. It is fine. Sir, you have a 45 minutes time.
Yeah.
Okay, thank you.
Thank you. Anyway, actually a very good afternoon to all of you. I'm extremely happy to see that, the fuzzy graph research team in your university is celebrating 50th birthday of fuzzy graph theory. I'm extremely happy to see that. Actually, my request to Professor Paul and his team is we should celebrate this together. So we have to think about a big conference in India, somewhere in India in the near future, to celebrate it in a much bigger way. That is my request. Anyway,
Yes, sir, we are going to organize a yearly change.
Yeah, 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 that is it. Sir has already given me an invitation also on this.
Too much.
Yes, 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 that will be great, sir. Anyway, once again, I'm thankful to the organizers of this program for giving me an opportunity in this platform. Even though I don't like this online platform very much, I'm happy at this occasion because generally, we cannot deliver the exact content through these online platforms. So, also, I don't know what are the basic material delivered today's morning sessions. So today I will be talking about one particular area that is not a new area, that's an old one. I will try to tell you about the development of that problem. Before moving to that, I would like to tell you one thing. See, you may be aware about the sudden death. Actually, indeed, it is not so sudden, but still unexpected death of Professor John Nelson Moderson of Creighton University. Actually, as we remember Rosenfield as the father of fuzzy graph theory, see, even though Rosenfield introduced fuzzy graph theory, most of the works, I will stress that, a huge amount, a good volume of the works in fuzzy graph theory was developed by this particular man. You can see he died at the age of 91. I have started a collaboration with this Moderson before 10 years at the age of 81. And on the previous day of his death, we submitted a book to Elsevier for publication. You won't believe it. A textbook on fuzzy graph theory. He was such a productive, such an excellent mathematician in the field of fuzzy graph theory. So let us pay together tributes to John Nelson Moderson at this occasion. And if you go through few of the books authored by him, anyway, we have authored nearly 12 books in the area of sustainability, fuzzy graph theory, and mathematics of uncertainty. Even though the titles are something like sustainability, etc., most of the content are in fuzzy related areas, especially in fuzzy graph related areas. So there may be research scholars anyway in the audience. So I have an advice to you. Please go through these books. You will get n number of problems. So that fuzzy graph theory book, the first one and the last one, are the same actually, but okay, there are some other books also. So there are 12 books written as a series in fuzzy graph theory and areas related with fuzzy graph theory. So those students interested to do research in fuzzy graph theory should go through these books. They will get enough problems, challenging problems. See, in most of the books, Moderation provided new theory actually. He didn't take any content from anybody else area and work. See, we develop the content, put them in these books, and publish the books. And in that way, anyway, if you go through his books, you can see that he is really one of the, what I can say, you know, major contributor to the field of fuzzy graph theory. So, once again, on my personal behalf and on the behalf of all people admiring fuzzy graph theory, doing research in fuzzy graph theory, so pranam to Giant Moderson. And let me continue. I'm here audible right now, isn't it? Hello, I'm just verifying. Hello? Hello? Am I audible?
Yes, sir, you are.
Okay, thank you. I'm just verifying because there was a power failure here. All right. So today,
Yes, everything is fine now.
thank you.
But if
Thank you.
you
Thank you.
if you're not listening,
Now, anyway, today I will discuss one problem today. See, among different streams in fuzzy graph theory, I will point out few major streams. One is connectivity in fuzzy graph theory. Actually, when we study graph theory, we used to study many things like directed graphs, then Hamiltonian, Eulerian, different kinds of things. We have seen some algorithms there, like Dijkstra's algorithm, then so many algorithms. Those algorithms are used to find shortest path sometimes longest paths, sometimes, I mean, we have several algorithms. But all these algorithms are working with weighted graphs. There is a book here. You can see one, two, three, the fourth one, weighted and fuzzy graph theory. I would like to request you to read that book because that is written in a weighted graph perspective. So why a fuzzy graph as a weighted graph? See, even though mathematicians like Bondi and Murty studied algorithms, they did not provide enough theory for that. Later, computer scientists used those algorithms for several applications like quality of service problems, maximum bandwidth problem, then I mean maximum widest path problem. There are several such problems belonging to different fields like I mean computer science, transportation networks, optimization theory, etc. Actually, fuzzy graph theory did fill that drawback. Actually, when we have a weighted graph, I mean, when you have a fuzzy graph, you can approach it in two different ways. One, a graph obtained in a situation where ambiguity do exist. So when there is an ambiguity among the vertices, you will make a fuzzy, I mean, a membership function. You will construct the vertices using them, assign membership value. Then you will construct an edge function, assign edge membership value. In that way, you can say the primary objective of a fuzzy graph is to address uncertainty. For example, if you are constructing a road network or a railway network, most of the parameters will be uncertain. But once you construct the graph, it becomes a weighted graph in one perspective. In another perspective, when you change the values, etc., in internet and all, there may be uncertainty still persisting. But we can consider a fuzzy graph once it is constructed as a graph, as a weighted graph also, and all the results we have developed for the last 50 years are applicable in interconnected connection networks. Now, this is the era or period of networks. For example, internet itself is a huge network. Only fuzzy graph theory can address problems in internet because weighted graph theory was not addressed in graph theory properly. If you read some books like, say, the old Bondi and Murty, you can see there are some chapters devoted for weighted graphs, and only limited discussions are available there. And frankly speaking, this one, two, three, the fourth book is the first book written exclusively for weighted graph theory. So you can connect fuzzy graph and weighted graph, so new results will emerge. So connect, connectivity is the first stream. Then metrics, extremal problems were studied by several authors. First, I am trying to tell you about the fuzzy graph part alone. In fuzzy graphs, connectivity is dealing with the weights properly. See, when there is a network, the weights do matter. See, for example, I'll tell you, suppose you are considering a small portion of the internet in in Korea and a portion in India. We can, yeah, pardon? Oh, yes, it is. Now, what happens? It's working, right? Yeah, because it was not work. I mean, still for a few minutes. That's why. Okay. Anyway, I'm coming to this. After 2 minutes, I will come to the slides again. So there are several streams of research in fuzzy graph theory, out of which connectivity is our area. See, myself, my students, my teacher, their students, we have a big group in Kerala dealing with connectivity models. But there are many pockets in India where fuzzy graph research is going on. There are some pockets in Tamil Nadu. Of course, in Bengal you have plenty of very nice groups. So we have several streams. Even though I have no time to talk about them, I will be sticking on the first stream only. The connectivity was the concept attacked by us first. These definitions might have been presented before you by Professor Noel today morning. I hope so. So I am just to show you these slides and will skip them totally. The definition of fuzzy sets familiar to all of you. I hope all of you civil students today are, I mean, may have some basic ideas in fuzzy graph theory. Okay. Anyway, yeah, why fuzzy graphs? I have already answered to this question. When there is a uncertainty among the description of objects in the picture, we use fuzzy graph models. I have already told you about that. Anyway, you might have seen this picture or this definition today morning. A fuzzy graph is defined as indeed a pair of functions actually. Of course, there are some entities involved. That is set, membership functions on vertex set, membership functions on edge set. So there are different varieties of possible edges in a fuzzy graph. So some cycles. So when you give weights, different types of cycles are possible. In ordinary case, there is only one type of cycle possible. A cycle whose membership value is 1 for every edge. But we have lot of variations possible here. So a lot of beautiful type of cycles can be studied. Now, for example, look at this. Bhutani and Rosenfeld introduced this concept in 2003, Lockerman cycles and multimin cycles. If at every point of a cycle, if a minimum edge is appearing, so minimum is appearing locally, that's called, okay, it is Lockerman. Okay, and multimin means, of course, if there are more than minimum, then we have multimin also. So when you have two cycles like this, we get another beautiful structure called arc disjoint or edge disjoint fuzzy graphs. Okay, no two different cycles share a common vertex. Now, let us come to the main theme of discussion of today's session. Actually, my aim today is just to tell you how the concept of block in fuzzy graph evolved, what was the timeline of research in blocks, who did the first work in blocks, second work, third work, finally, do we characterize the blocks completely, and what are the possible variations of blocks, and what are the future research left in blocks. That is my intention. So look at this. This see, so you imagine this dots as certain, you know, servers. Suppose you have a big building, our computer science department or even our, internet people will, you know, they will bring, they will, I mean, have some routers at different points, and the routers will be connected either by line, sometimes by Wi-Fi. That also is a virtual line. So the bandwidth possible, maximum bandwidth from a router A to B. That is what is defined in fuzzy graph theory as strength of connectedness. It was the idea of Rosenfeld. Look at this graph, for example. Very simple. We have given colors also. See, from vertex V3 to the vertex V1, you consider all paths. The strength of a path, that's the capacity of a wire to carry the data. And it is normalized. I told you an example about Korea and India. In Korea, they have high capacity networks. So they may have, their data is above 5G now. In India, we have 3G or 4G only. So when we compare two portions, it is difficult to say which country is better, which part of the country is better. So we should normalize it anyway. without thinking about the fuzzy part. When we normalize, still we get a fuzzy graph as per the definition. As per the definition, because there are discrete as well as continuous fuzzy membership functions. This gives a discrete membership function. So this may be arrived, this picture may be arrived from a real world situation. Four routers connected with four lines, I mean wires. So there is no fuzziness involved, but still it is a fuzzy graph. So here this connectivity is very important. How to increase connectivity? Suppose my neighbor wants more internet. How we can give? That's called a quality of service problem. We can think about giving a, okay, more connectivity. We will think about such things after some time. So here, you between 2 points, there may be several paths. So the minimum of, because if there are two pipes connected of different diameters, the maximum water it can carry by these lines. Anyway, you imagine these pipes, the maximum data that can be carried by these lines along a path, it will be the minimum. So if there are three paths, this minimum should have a maximum. That is exactly the famous parameter called maximum bandwidth in an internet network or a computer network or in a mobile network. So for mathematics people like us, it is strength of connectedness. Also for transportation people, it is the widest path. There are a lot of variations in different branches of science and engineering. So in this way, a path with capacity is equal to the maximum bandwidth. We call it as a strongest path or a path of maximum bandwidth or a widest path. There are so many names associated with such a path. Now, anyway, suppose we have high internet connectivity, but suppose there is a power failure in one part of the campus. What will happen? Some routers will fail. They may not be able to transmit data. Our routers are the nodes. So actually, but still, suppose we have 3 points A, B, C, B failed, still there may be traffic from A to B. So some routers may be vulnerable in a sense. When they fail, the data processing will become slow, the data flow will become slow. But it is not, we have faced that situation many times in our life, right? In our mobile phone, in our computer, in our internet connection, in our TV channels, even in the bus. When you travel from A to B in a bus, if there is a traffic block, if there is a bottleneck, you know what's a bottleneck? If there is a bridge, say for example, that's a bottleneck. What's the problem with the bridge? If it is four line traffic and the bridge may be two line, so there is congestion there. So there can be vulnerable edges and vertices. So they are respectively termed as fuzzy vertices and fuzzy edges or fuzzy bridges. That possibility is not there in the classical graph theory. Also, some failures will be affecting the entire graph. Some failures will be affecting only the endpoints. Some failures will be affecting only the endpoints. I mean, some other endpoints. Anyway, there are several different varieties of vulnerable nodes can be defined and studied. For example, yeah, I will give you some of them after some time. So that option is not in graph theory, but this option is important in network theory. In future, when we need to develop a high-fi internet network, we need to consider the nodes where there is a chance of failure. We should consider a wire. Sometimes, some wires will be lifted by our JCBs when they construct a building, right? So, through that removal, nothing will be disconnected, but something will be affected. That is what is the motivation behind. In most of the modern network, see, disruption of the network is not common. I mean, the talk complete disruption is not common, but reduction in the capacity flow, I mean, in the flow of traffic is very common. That is the motivation in defining this fuzzy bridges and fuzzy cut nodes. They were all defined by Rosenfeld, right? Okay. Now, you might have heard about fuzzy trees. I am not going to talk about fuzzy trees. A very beautiful structure. Fuzzy tree can be a cycle, but in classical theory, a tree cannot be a cycle. Fuzzy trees can be. Fuzzy trees are indeed a representation for, I mean, minimally connected portions. Even if there are cycles, there is no problem. It will be minimally connected only. Some, like the classical case, minimal flow only. When we cut and wire, the flow will reduce drastically. So that's minimal connected. Suppose even if you cut the wire, nothing will happen to the flow. That is what we call a complete fuzzy graph. You know that definition. Here, when you cut it, drastic difference will be there. Okay, I'm not going to the definition of facility because that is not our aim. Since it is in the presentation, it was prepared many, many years before. Sorry for that. There are plenty of new topics also, but I don't know what exactly is the level of knowledge of the audience sitting in front of me. That's why I took this topic. So don't get bored by this. Okay. So I'm not going to talk about facilities in today's session, but this concept was very important by Bhutani and Rosenfeld in 23 in 22003 said certain edges are strong in the sense even if you remove that edge, the flow from the end vertices will remain the same. Hope I understood that. You understood that. Even if you remove it, the flow from the endpoints, suppose there is a bridge, endpoints are A and B. I'm telling about a layman's classical bridge. Suppose bridge is gone, bridge is collapsed. So suppose the bridge is not affecting the flow from the endpoints, the town A on the left side and B on the right side. Okay. Suppose it is okay. Uh, there are three possibilities there. Suppose that bridge is the only connection between A and B. Then there is no flow possible. Or the connectivity between these two towns is exactly the flow through the bridge or the capacity of the bridge. That is the strongest one. In that case, we say it is alpha strong edge. That edge is very, in some sense, it's very strong because if you cut it, nothing will actually, even the connectivity will be very, very less, or the edge weight is more than the connectivity between the endpoints. Suppose nothing happens to the connectivity. Initially, 100 cars were flowing from A to B per hour. Now that bridge is gone, still 100 cars are going through some other routes. So in that case, we call it a beta strong arc. And this alpha and beta generally are termed as strong edges. And suppose that bridge is a cycle bridge only. Only cycles can move along the bridge. So the flow is very minimal. And if you even if you cut the bridge, nothing will happen. Actual flow will remain the same through some other. So the membership value of the bridge, if it is less than actual flow from the town A and B, that's only a small shortcut kind of thing. That's an irrelevant road, and we call it as a delta edge. It does not mean that delta edges are weakest edges. Don't think in that way. That way, it is not necessary that the weakest edges are of this quality. No, there can be further weakest edges in the graph. Okay, and this also was a concept by Rosenfeld end node. So end node has a concept like this. See, when an edge has, suppose there is a strong edge, the end vertices are called strong neighbors. A vertex can have n strong neighbors if it is attached to n strong edges. So if a vertex is connected to only one strong edge or only one strong neighbor, it becomes a fuzzy end node. Look at this graph. This yellow are these are fuzzy cut nodes. We have already discussed what it is. These are fuzzy end nodes. So this is not a strong edge at all. Look at this point 2. It is a negligible arc. Look at this. The actual flow from this V3 to this portion is minimum of zero point 0.3, zero point 0.5 and zero point 0.6. That's only zero point 0.3. So that is more than the just weight. So these are delta arcs. So delta at so this point is connected to only one. Actually, this is only strong edge. So there's only one strong neighbor. So that becomes a fuzzy end node. Okay, I told you about complete fuzzy graphs, an equivalent version of graph. I mean, a complete graph in graph theory. Okay, if you replace the weights by one, vertex weights by one, by this definition, it becomes a complete graph. So that is a falsified version of this. Okay. Now, yeah, these are the definitions which I just to go through this. An arc is alpha strong if then the edge weight is this, delta beta strong if it is equal to this, delta if it is this. I told you it is not necessary that it is the least weight arc. So if there is If our arc is not least weight, we call it as a delta star arc. Okay, this is an example. You can go through this if you want. Because of time, I am not going to discuss about this. Okay, some characterizations I'll provide. Look at this graph. So how to identify that an edge is a fuzzy bridge? Very simple. All alpha strongs are fuzzy bridges and vice versa. All bridges are alpha strong edges. Indeed, they are one and only, they are same only. Okay, so look at this. We have marked alpha, beta, etc. in this case. So it is easy to say that all alpha strong edges are fuzzy bridges and vice versa. Okay, and there is another very nice formulation. An arc actually, yeah, this look at this. An arc is alpha strong if and only if it is in every maximum spanning tree. You might have understood the proof by now, right? Because every alpha strong is a bridge, and if an edge belongs to every maximum spanning tree, an edge belongs to every maximum spanning tree, it by the removal of that edge, all maximum spanning trees will break and the graph will break or reduce the, I mean, capacity, I mean, this connectedness. So this is an interesting result, and we can say if an edge belongs to every maximum spanning tree, it is alpha strong. So anyway, this is a result related with the number of maximum number of maximum spanning trees. Say this theorem is about a fuzzy tree. An arc in a fuzzy tree is alpha strong if and only if it is the arc of the unique spanning tree. It's a corollary only, but we wrote it's a theorem. From the previous theorem, we can say for a fuzzy graph, by definition, fuzzy tree, there is only one maximum spanning tree. So if so, every edge in that maximum spanning tree are alpha. So look at these pictures. So this is a delta arc. So these three are alpha strong edges. So this is a fuzzy tree. Okay. Yeah, of course they are fuzzy bridges. And look at this definition. Not definition, remark 1. This result was proved by M.S. Sunida and Vijay in 2005. If G is a fuzzy tree, then removal of any alpha strong arc reduces the strength of connectedness between its end nodes, also between some other pair of nodes. It's an interesting result. In a graph, in a tree, fuzzy tree, it will affect the flow between some other pairs also, not only between the end of those, I mean, the particular edge. Now we have a characterization of fuzzy trees using these arcs. A fuzzy graph is a fuzzy tree if and only if it has no beta strong arc. We already discussed it. Only bridges and these delta arcs will be there in a fuzzy tree. So if a graph do not contain beta strong edges, it is clearly a fuzzy tree. Okay. Now, there are some other simple definitions. A path is called alpha strong if all arcs are alpha strong. A path is called beta strong if all arcs are beta strong, etc. Okay. Now look at this. I will go very quickly. G is a fuzzy tree if and only if there is unique alpha strong path between the two. This is a generalization of the classical result. If in a graph, if it is a tree, there is a unique path between any two vertices. Okay. And this one is nice. That T be a spanning tree of a fuzzy graph, then T is a maximum spanning tree of G, if and only if T contains nodal arcs. Okay. Further, a maximum spanning tree is unique for G if and only if T contains no beta strong arc. In other words, it's a tree. Okay. Suppose G is a cycle, G star is a cycle, then there are two options for G. You know that? Okay. G is a fuzzy cycle if and only G has at least two beta strong arcs. Okay. Now, yeah, these are all some results related with these cycles and trees. And unfortunately, since we have only 10 minutes left, I will go to the actual problem. Our actual problem was different. Our problem, anyway, you may be familiar with all these things. Complete fuzzy graph has no delta arcs. There is at most one alpha strong arc in a complete fuzzy graph, etc. etc. See, today's actually, I'm skipping these theorems just because of time. This is what is the topic for today. So, it is a problem of absolute, magnificent importance in computer science, in traffic networks, in internet, etc., to identify the vulnerability of nodes. Who are the vulnerable nodes? In a huge network, we need to write algorithms to determine the vulnerable nodes. When more data pass through a node, sometimes it will fail. So finding the vulnerable nodes and doing make the patchwork will strengthen the network. So that is what is required in the current future current network. It is what that's what required. So characterization of blocks is absolutely important. Let me tell you frankly, till today it is an open problem. We have not characterized the blocks completely. There are no algorithms which will extract blocks from a big normalized fuzzy graph kind of network quickly. So as you know, a graph is a block or fuzzy block or something like that if it has no fuzzy cut nodes or vulnerable nodes. Definition was provided by Rosenfield itself. Okay? And of course, we have, I told you, fuzzy cut nodes on reduction will reduce the strength of connectedness between some pairs of vertices, etc. Look at the progression of the results on blocks. Rosenfield in 1975 said a block may have fuzzy bridges. So that itself says a block in classical theory and block in fuzzy graph theory are entirely different. Because in fuzzy bridge, in the classically it is a bridge, a complete graph may not have a bridge. Okay. If between every two nodes of a graph, if there exist two strongest paths that are internally disjoint, then G is a block, but the converse is not true. Actually, this okay, also was given by Rosenfield, the same paper. Okay, if there are two rods of equal capacity between every two pairs of vertices, unfortunately, that is not practical. So you can ask me or to anybody, then why can't we construct two highways of same capacity between every city? It is too much time consuming, space consuming, money consuming. So that's not practical. So we should think about a better option then. So this practically is not feasible. If between any two vertices of the graph, there are two internally disjoint, that means if you're coming from Bengal to this Kerala, one you should come along the coastal line, other one you will go to somewhere else in the interior of the country, like you will go to Delhi, then Mumbai, then to Kerala. In that way. Okay. So this is practically impossible. So later in 2005, another characterization came. So that was by Sunida and Vijay Kumar. See, look at this. G is a block if any T node such that U is not a fuzzy bridge. You can exclude fuzzy bridges, then other nodes should be joined by two internally shown strongest paths. That's one characterization. That's already it is there in the literature. Only difference is they excluded fuzzy bridges. Third one, for every three distinct nodes of G, there is a strongest path joining any two of them, not containing the third. So anyway, this also is not practically feasible. It was the first full characterization of blocks in the literature. It was given nearly 20 years before. Then, actually, in the same year, I'm leaving this cycle business. Later in 2000, maybe 5, 6, that period, uh, myself and MS Sunida came up with a set of necessary conditions for a fuzzy graph to be a block. So what we said is, if it is a block, the following conditions are equivalent. So now, once we have this much conditions, from where I got this much condition? We simply referred Harare. In Harare, there is a theorem regarding blocks giving several equivalent conditions. And what we understood is these conditions do hold in blocks, but not the reverse way. So, once we can prove this, we will have another question. In which category of fuzzy graphs all these conditions will have inverses? We will come to that. See, this was a very long proof. We proved all these things. You may refer the my previous papers. You will find the proof of these conditions. Okay. Actually, then we failed to write all the seven conditions associated with a block in fuzzy setup. We thought about another kind of cycles. See, a cycle joined by or connected by or obtained by two strongest strong paths. Not only that, if you take any two vertices in the cycle, they should be connected by two strongest strong paths. you can exclude alpha strong edges. That means between any two vertices, there should be a strong two strongest paths joining them. So that means whatever way you take, you will find two different strongest paths, excluding these bridges. Such a cycle is called a strongest strong cycle. Strongest did not work, and our previous necessary conditions were using strong cycles. So strong cycle also failed to give a reverse condition. So we clubbed them and took strongest strong cycles. Okay. Anyway, these are same only. Now we were able to prove certain equivalences like this. Look at this. When the underlying graph is a cycle, the block is equivalent to a strongest strong cycle, and that is equivalent to a Lokamin cycle. That's the first step in the direction of finding more results. So, as you know, a cycle is the minimum structure in which we can discuss very nicely. So, then we came up with another one. If graph is edge disjoint, then also block SSC and Lokamin are the same. We have no time to explain more. Later on, yeah, we obtained another characterization, but not involving all the seven conditions. Final two conditions failed. Only five conditions were involved. See, look at the statements. Here, G is a block. For any two nodes x and y of G, there exists a cycle containing the nodes x and y, which is formed by two strongest. The wording is very important. For any two nodes, there exists a cycle containing the nodes x and y, which is formed by two strongest xi paths. Then, okay, and all these things were in graphs without bridges. So,
Hello, sir. I'm sorry to say that I have only 5 minutes.
okay, thank you. I will stop in five
I'd
minutes.
like to summarize your
Okay,
content.
okay. So this one also was not a full characterization. So, but we obtained a beautiful results in, yeah, I don't remember the age. If any two nodes of a fuzzy graph G lie on a common SSC, then it is a block. That was a reverse problem. That was a reverse problem. Okay. Now, finally, we realized that there is a category of graphs called theta fuzzy graphs, in which the reverse conditions are also true to some extent, not in full extent. For that purpose, we define theta evaluation, introduce theta fuzzy graph, some new type of connectivity, etc. And that new connectivity is called cycle connectivity. That will tell you how cycles are, what is the cyclic flow in the graph. Okay. And using cyclic flow, we have theta fuzzy graphs. And theta fuzzy graph will address many other problems in graph theory. And this lemma was the key to the solution. If G is a theta fuzzy graph, then any strong UV path, such that UV is not a strongest path, okay, not a fuzzy braid, is the strongest path. Any strongest is strongest. So any strong cycle is strongest cycle, strongest strong cycle. So our previous necessary conditions now becomes necessary and sufficient conditions. So we proved one to these seven conditions for a subcategory of fuzzy graphs called theta fuzzy graphs. Okay, now if you are given a theta fuzzy graph, you can write an algorithm, extract blocks. You can say these are vulnerable nodes. You need more attention on those nodes. And but this also you can think about. But this is only a subcategory of fuzzy graphs. So this may not be the maximal category. Sometimes you may be able to find a mother category where all these conditions are equivalent. That is your task. Okay, that exactly is that's an open problem. If somebody is interested, please read these theorems, and either you have to prove that this is the maximal collection where all these conditions are necessary and sufficient, or you have to prove that there is a class derived out of these, okay, in a set of all fuzzy graphs in which this fuzzy or I mean blocks can be easily characterized. So characterization of blocks, an algorithm for blocks will be a very good contribution from mathematicians to all interconnection network people, traffic network, in networks, etc. So anyway, if you want, more kinds of blocks were also studied thereafter. Something like transitive blocks. Transitive blocks and their application interconnection networks is a very good paper published in fuzzy set and systems. Then certain new critical blocks, that's another kind. So many new things were introduced on the way. Anyway, I'm not going to the remaining portion of this presentation. So we are going to stop from here, stop at this particular point. So this is the history of blocks in fuzzy graph. Not completely, and we have progressed little further. If somebody is interested, they can contact me. We can do some research in this area. So thank you very much. I'm going to stop here. If you have any quick questions, please ask me.
So thank you. So thank you, Professor Mathew, for your completely good thoughts. So
Thank you.
now the discussion is open to all for any questions from the audience. Do you have any questions? Anything in your mind? Okay. Sir, any future direction for the researchers, future works, possible area from your side, any suggestion?
There are many suggestions, as I told you. See, the problem I mentioned today is one of the basic problem actually. It was studied in 2005 to 2010. Thereafter, there were lot of contributions by lot of mathematicians. In say, for example, T-norm fuzzy graphs. You can ask me why we take a minimum of vertex weights as the edge weight in a fuzzy graph. It's an interesting question. Why can't you generalize it with an arbitrary? Instead of that, you can have plenty of options. So we have introduced a paper called T-norm fuzzy graphs. So that's a very good area. It is really difficult actually, but still it will be a wonderful area. Also, see, as I told you, when I worked with Moderson, each of his papers were carrying new results. And you might not have seen those results, frankly speaking. But they are all available in his books. There are two more books to come actually. They are in press. One is in Elsevier and one is in Springer. And we will publish them in 2026 maybe. So if you want, I can help you. Even I can give you the soft copies of the books, etc. So there are hundreds of new concepts. Okay, you can work with those things. I have one suggestion. Don't publish your articles in very low quality journals. There was a trend in fuzzy graph theory area to publish papers in very low quality journals. So we should publish in high ranking fuzzy journals. So you will get more visibility and more people will read them. That's an advantage. And as you know, even today, some mathematicians do consider fuzzy graph theory as a secondary subject. See, in many conferences, I was not allowed to present my topic. They were graph theory conferences. They said fuzzy graph theory is untouchable to us. Please don't bring any fuzzy graph papers here. I was surprised. I was sad also. I have told to Professor Pal once again about this. Okay. So we should work together and we should show our strength. Now, after 50 years, it is a very strong subject. We should have a very strong collaboration also. I am ready to come to you. Just call me, I will come. I would like to have a talk at your institute. So we can have discussions. Anyway, this online platform, we have limitations. So we will have mutual, and I mean, we should share the results. We should work more. We should work with more practicability and visibility so that one day others will respect us. Since we are running out of time, I don't have much now to say, but publish nice results in nice journals, have more collaborations. Don't also there are so many variants like vague fuzzy graph, Pythagorean fuzzy graph. Few of them are similar only. Before writing research, you should think whether I am writing something new or not. So writing parallel works that also is not appreciable. So write genuine results. That is my advice to the scholars sitting in front of me. That is possible so that people will appreciate us. They will recognize our contributions. Anyway, that is what I have tell you. People like Rosenfeld and Moderation, they have anyway laid a very strong platform in front of us. Just walk, and you will be flying with colors. Thank you.
Thank you, sir, for your encouragement. So, Professor Mathew, this question is come from Dr. Sunil from Tamil to Mahavishal. Of course, Sunil is scholar of Professor Pa.
Pardon,
Okay, so
actually,
any
that question
questions?
was not so clear. Could you please repeat it, sir?
So, Dr. Sunil,
Ah,
so thank you very much for your suggestion for the collaboration between us. Okay, so we will go for that in next discussion. Okay, we'll discuss how we can go for the
yes, yes.
collaborative work. And no, some years ago, the Jet Pachise was invented or linguistic jet or linguistic jet graph like that, or Shoman will deliver today just after your lecture. Dr. Shoman will deliver this lecture on quantum budget graphs. Okay, so this is another new concept on the budget graph. The time distribution are posed on the vertices and edges. So the statistical analysis are doing on this particular type of. So here we can collaborate with and other issues because you have published a lot of papers no, from Sunita, yourself, another your research scholar. So in short time we can discuss in short duration we can discuss how we can go for that. And we can also organize a joint international market. Okay, thank you very much for your nice presentation. And
Yes, sir. Repeat again. So all the very best for the program. Actually, once again, I am very happy that you have organized such an event at the 50th anniversary, and we will do more in future. So we are also planning to organize an international conference if possible. I will let it details
আচ্ছা
later.
আচ্ছা এতক্ষণ ধরে জাস্ট আমি বলছি যে ওটা অর্থই অর্থই কেউ পরে বলেছিল আমার ভয় আমি মনে হতে পারে আমার থেকে যাচ্ছে তাহলে আজকে চুপ আমি চুপ থাকতে হবে যদি কোন তুমি আজকে চুপ